So the presentation today is what is, or 3D printing, an overview for robotics. So first thing I want to go over, what is a 3D printer? Do you guys see this little screen thing? You guys read the slides now? Cool. So because Merriam-Webster has everything, that seemed like a perfectly reasonable thing to quote. So the manufacturing of solid objects by deposition of layers of material, such as plastic, in accordance with specifications that are stored or displayed in electronic form as a digital model. So just based on the dictionary definition, I'm going to have some questions for the chat. So, is this 3D printing? Let's see if I can view the chat. So you guys see what's going on there? There's a concrete castle built, and that is happening. So what do you think, Kaya? How'd they do? What's the general consensus?
There is no consensus. Oh wait, here it is. People are saying yes.
Yes. So everybody's saying yes, or a few people are saying no?
1, 2, 3, 4 yeses and no no's so far, I think.
Okay. So if you haven't, so if you've answered, let's check. Maybe. So it's a solid object. As far as I can tell from that picture, yes. Is it deposited by layers of material? From this picture, the answer is yes. And because this would be, I believe, a CNC process, it was probably stored and displayed in an electronic form as a digital model. So yeah, this giant castle in this guy's backyard was most likely true 3D printing. How about this? So what's our chat consensus there, Kaya?
People are saying no.
No. Okay, I'm gonna ask why on there too. So who's gonna type up why?
Okay. That might take people a second. Because it is food made out of ingredients. Electronic model.
So we got someone saying it's not printing because it's food, and we got somebody saying it's not an electronic model. Are those the main answers?
Those are the two answers. Oh, and you need filament to make a 3D model.
Okay. Anybody else?
No.
So, is this 3D printing? Most everybody was right. It is not. But 2 out of 3 of those explanations were not quite correct. So somebody said you can't have 3D printed food. And that's actually not the case. You can definitely 3D print food, and that's becoming kind of an emerging thing. Because food is a solid object. It can be layers. And if you decide to store it in an electronic format as a digital model, that can definitely be 3D printing. Someone else said you have to use filament. And we're actually going to go through, even today, and show you popular 3D printing techniques that do not use filament. So that are very much 3D printing, and one of them is going on in the background. You guys can see that one. The person said it wasn't sort of electronic format. Yeah, you're right. Anyway, so we're going to go through common types of 3D printing. We've got FFF, or FDM 3D printing. We're going to do SLA 3D printing. And then we're going to talk just a little bit about SLS 3D printing or DMLS 3D printing. So we're going to start out with fusion deposition modeling, which is FDM, or fused filament fabrication. So the reason there are 2 names, they are the exact same thing. But the company that invented this technology copyrighted the term fusion deposition modeling. So the rest of the community will typically use FFF to not violate that copyright. So this is our really common 3D printer. You guys are going to see this at McCutcheon quite a bit if you get to go into class. Mr. McKeever, Mr. McKee, and Mr. Ressler all have at least one of these types of 3D printers. Currently, it's our only type of printer used at McCutcheon. Not necessarily the only type you have access to, but it's the only kind that we actually have at McCutcheon. It's really convenient because it allows printing from a lot of different types of plastic. It's a relatively clean process, and the printers are relatively inexpensive, and the filament material is also relatively inexpensive. In contrast, we have stereolithography, which is SLA. So the person that said we've got filament, this is a type of printer that does not use filament. It actually uses a liquid resin. So this is actually a pretty common 3D printing type as well. It's used by some consumers and different businesses. And the way it typically works is you have a special chemical or resin that is hit with UV light, and when it's exposed to UV light, it hardens. So you can do that strategically to make a part grow. The downsides to this is it can be a messy process. There's toxic chemicals involved. You got to use PPE to actually do this process safely. And typically you'll find that the printers are smaller than an equivalently priced FFF 3D printer. So usually you'll see like a 2-inch by 3-inch, 3-inch by 4-inch 3D printer area rather than the larger area. But these printers are pretty inexpensive too. You can do pretty well for about $120. But the resin, the material you use, is more expensive than you would find in your common FFF 3D printer. So it's about trade-offs. The advantage of this printer is, as you can see from some of those pictures, you can get really high detail in your parts. And our third type for the overview is going to be selective laser sintering or direct metal laser sintering. So when you hear people talk about metal 3D printing, there's other methods of this, but this is typically what they're talking about. This is emerging technology, typically for businesses. So this printer, it would be unlikely that many high schoolers would have access to a printer. Not saying you guys can't get parts made with this technology. SLS 3D printing typically uses nylons. It uses a plastic, and it actually lays sheets of powder down and then hits them with a laser. So that creates your 3D parts. Which is same idea using layers, building solid objects. Direct metal laser sintering is a very similar process, but it's actually using metal powder. So with this process, you can get really high detail parts in plastic or in metal. The downside to this is these are really expensive machines generally. These machines can cost thousands of dollars, and then the powders are actually really expensive. And from my understanding, metal powders are not reusable. So you're using a lot of material every time you make this, because you got to fill up the bed the same size. But if you need the really strong metal parts, this is available to you. And if we ever needed parts like this, there are several online places where we can get parts ordered to our prints. So this is a technology that may become available if we want to use metal parts. So more questions. If my goal is to make these high resolution gaming pieces, what kind of printer should I use? And check the chat.
People are saying the resin one.
The resin one. Anybody actually use the right acronym?
No.
No, the resin one. So the resin one would be correct. So reason we want to use that, so it's SLA. So this is typically your highest detail for smaller parts. This is actually a real resin print right there. Typically you can get higher detail on this kind of 3D printing. And there's in little plastic miniatures, there's really no need for specialty materials. As long as you're reasonably strong and they hold together, you're generally fine. Next time, I'm trying to make a turbine for an aerospace application. What kind of printer should I use?
The one person says the metal one, the metal powder, okay. Nylon powder.
Anybody else?
Somebody said DMLS.
They actually got the acronym right. That's
Yes. I said the metal lasery one.
the metal lasery one. Okay. Yeah, that would be a good choice if you're trying to make aerospace parts. Why? Because you can use high strength metal alloys in this. So you typically have to control pretty tight tolerances in the aerospace industry. So the only one you're really going to have much of a chance on is going to be metal laser. And in aerospace applications, you might find that although this is expensive, you can save a lot of money than traditional machining. Even some of the crazy alloys that are used in the aerospace industry are very difficult to machine, and a lot of times is easier to do with an additive process than a subtractive process. So let's talk a little bit about 3D design rules. Does everybody understand the different types of 3D printers? I guess I should say first. Are there any questions? If you have questions, type them in the chat. Nobody, Kai?
Wait. Somebody says, why are there different ones?
Why are there different kinds of 3D printer? Because there's a lot of ways to make different parts. So there's a lot of pros and cons to different types. So FFF 3D printing is really nice for just low cost things. You can need quick prototype parts. It's really great. You can do a lot of cool things with different materials. Resin 3D printing has become really popular and just uses a completely different technology to get high detail parts. And then with metal laser printers, you can make metal parts, really high detail. So there's, depending on the parts you're trying to make, you want to pick different 3D printing technologies. And there are a lot more than the three that I named, but I tried to name the three most common ones that you guys would be exposed to. Hopefully that answers that question.
He said, okay.
So the rules do change between 3D printing technology, but more or less are pretty similar. So I'm going to teach you the FFF rules, but a lot of the SLA rules still apply. So parts need to have a flat bottom so they do not stick to the bed. Little tiny bases on parts are probably not going to stick very well to the bed and are going to break away and give you a big mess. So hopefully that makes sense. Overhangs. So what an overhang is, if you have a part sitting on the bed, you don't want to go more than 30 degrees or 45 degrees out from that part. Otherwise, you're likely to have issues. Bridges, which are these guys in the corner, are okay if they're short. You can usually get away with that. The longer the bridge, the worse it's going to turn out, though. So depending on your material and stuff. So designing around those is generally ideal. You'll find from this picture, vertical holes are typically okay. You can, even though that goes against the overhang rule, you can usually get away with that. And then islands and peninsulas, I'm going to say. So an island is meaning you're trying to 3D print a thing in air, or a peninsula where only one side is touching your object and you're making a large flat object, because that would be a 90-degree overhang. Those almost never will work in a 3D print. Now, sometimes you guys are going to want parts that use the things you can't do in a 3D print. So the trick there is you use support materials. This is how we break our rules. Support structures, like you can see here, go under the part to support the parts that need it. So you have to follow those rules with 3D print, but we can add these support structures that go ahead and build more material to make our parts follow the rules. And then when the part's done, we can just remove the parts. You've got soluble support material. So this is dissolved in a chemical bath. There's a few different options for that. A lot of the more common ones just use water. A few of them actually use more toxic chemicals than that. Breakaway support materials work just by using the exact same material, and you can break it away from the part. Soluble materials typically give you a better end, but require more expensive printers and multi-materials. So sometimes that's an advantage, especially if you're going to do complex parts. When we talk about SLA 3D printing, that you're pretty much limited to breakaway supports. However, it's pretty common that with SLA 3D printing that your supports come off almost cleanly. So using supports is usually not a big deal. I think that's going to bring us to slicing. So slicing is how we tell our 3D printer how it's going to make a part. So we can do cool things with settings. We can add strength. We can decrease or increase weight, and we can generally add supports. So I'm going to go through an example, and hopefully this works, about how we slice something for a resin type 3D printer. So here is the software. Resin's a little funny in that you generally don't print on the bed, but as you can see here, the software went ahead and designed the support material for me. So in this example, we're making the boat. These will probably get broken away very cleanly. And you can see in the background, this part's almost done. So I'll show you the post-processing on this too if that gets done quick enough. But this is pretty simple. So with resin 3D printing, we don't generally have as many settings as we do with FFF 3D printing, which is why I'm just going through it. Tricks here, we can do layer thickness. So pay attention, each layer on an SLS 3D printer is 0.04 millimeters. That's really small. So we can actually do finer than that, but we'll contrast that in a minute to what FFF can do. Our exposure time. So the way that works is there's a resin bath and there's light that shines on the bottom layer, and you keep building these light structures all the way up. So we expose the material to light for 10 seconds, then we turn off the light and pull it up, and then continue that process. So we need 10 seconds on, 1 second off. What that means is the time is really easy to estimate because the whole layer is done in 10 seconds no matter what. So the time of this print's actually really easy. It also means that if I were to do 2 of these parts, it would take the exact same amount of time. So if I were to go ahead and put one here, I think there's a button for that. No. Won't let me do it. But anyway, if I have 2 of these boats on this part, because of the same height, they take exactly the same amount of time on this particular printer. Now that differs from some SLA printers that use a laser, and that'll actually take a bit longer if you're using a laser to cure the material. Then you set your bottom exposure time. So the reason this one's a lot higher, so this is 2 minutes on the bottom 8 layers, that's so it sticks really well. And you set how many bottom layers you want. So, and then when you're ready, you go ahead and just slice this. And we'll actually take a look at what this does. Well, it's slicing. Any questions so far?
Yeah, we just got a question. They said, is there a way to make a boat or anything that would require support without support?
Yes. So that can you make parts without support? Sometimes. Yeah. So typically support material is really important on this. We can sometimes orient parts and get rid of support material. And on this type of printer, there are ways to get around support material. Although I will say on these kind of printers, you generally put the parts at really weird angles is typically what's done because it lets it get less time on the screen and typically prints better. Also, the support removes almost perfectly clean. So we'll take a look at the preview of this so you guys can kind of see what's going on. So this is the first layer. So it's actually going to take the screen on the 3D printer and it's going to make that pattern. So it's going to turn these on. So it's going to allow UV light to be exposed here. And then anywhere that's white, it's not going to allow UV light to be exposed. And it's going to grow. So you guys can see here, this is the support material. So that's just growing up. And then you're going to generate your boat. And it's eventually going to go to the top. So as you might figure out the way gravity works, and if you can see it in the background, this actually makes the part upside down. So because you need the bat down, it'll actually pull the part out of the bat rather than just letting it be in the bat. Does that make sense? Any other questions? Anything, Kai? Everybody understands?
Nobody said anything yet.
Cool. So when that finishes, I'll actually show you guys how to post-process those parts. That's all set up in the back. But in the meantime, we'll start talking about FFF slicing. So, go back to PowerPoint real quick. So you guys see, he's not figured out. That's what we're making. So it's a cute little boat. Go to our example 1. We need to make this part. So the first thing I'm going to ask, and as I get this set up, I'll let you guys type, but will this part require support material?
People are saying yes.
Getting yeses?
I'm also explaining in the chat what it is.
So we're getting a whole bunch of yeses?
Yeah. And a lot of maybes.
Maybes. So let's talk about orientation first. So is this the best way to orient this part? Because we can change it. We can do that. So you guys remember, we need a flat surface on this part to make it. And we generally want to, if we're going to use supports, we want as few supports as possible. So what are your thoughts? Is this the best way?
Somebody said no.
No? That'd be a good answer.
No.
So we're going to pick a flat. So I think it actually imported is the best way. Does anybody see a better way to import it than that? Because you got a big flat side right there. Okay. We also need to talk a little bit, and I think here is about the best thing about layers and strength. So FFF 3D printing is the strongest on the X and Y axis, and about half the strength typically or more on the Z axis. What that means is we need to think about how our orientation of our parts will affect our strength if we have a choice. So what that means is if I were putting a load, breaking this in half, grabbing both sides and twist and breaking it in half, that's going to be easier for me to do if I grab, you see my mouse? I'm trying to use it as a pointer. Okay. So if I grab this side and break it, it's going to be easier than if I grab this side and this side. Also something to think about is this side is going to be pretty weak because it's built up with a whole bunch of layers, whereas this wall might be stronger if I put it on the base. Now, I'm not trying to confuse you. Sometimes we just have to make the parts, but it's something to think about if we have choices. So you do have two axes that are stronger than the third. So if I grab this side and bend it, it's going to be a lot stronger than if I grab the bottom and the top and bend it. Clear as mud?
Yeah, somebody said, so your question earlier about how that was oriented, if that's the best place, somebody said not unless you can make it as two parts.
So somebody wants to make it as two parts. We can do that. We can actually split that.
Can you do that in the slicer, or would I have to like go and do it in Onshape?
No, I just did it in the slicer.
Wow.
So yeah, that's totally an option. You'd have to glue the parts together, but yeah, that's what you want to do. That doesn't eliminate support material because you see we still have an island right there, but it definitely gets rid of it, or gets rid of some of it. So yes, we can break parts up and glue them together. Now, generally, I try to avoid using glue, so we could actually print this out in one part. But yes, that is an option. So any other questions up to this point? We've oriented our model.
Evan says, what about duct tape?
What about duct tape? That would work, but typically you're going to get lower quality parts if you just try to attach them with duct tape.
He says zip ties.
Okay. Kind of mute Evan for now. Anyway, so we can now go into print settings to take a look at what we might want to do. So there's usually presets, and for the printers at school, there are also presets. We can talk a little bit about what some of these mean and how we adjust settings. So the first thing I told you to pay attention to the 0.04 millimeter layer height on resin printers. On FDM printers, the finest detail I can do is 0.05, and that's only available, that's like super fine detail, takes a really long time, and most printers are not capable of that. Typically, we run things at 0.15 to 0.2. And that also kind of goes to show the point that resin printers are much higher detail. So when we design parts, thicker layers will typically produce stronger parts and take less time to print. Thinner layers are going to show better detail. So with this particular part, we probably want to run it quickly and we want to run it thick to get as strong as possible. And that's what this part's on the robot, and that is what we did. So we now have the shell. So you can see we've got perimeters here and we've got solid layers on the top. So if you want to make a part strong, you want a strong shell. So what a shell is you're going to have the outside a solid material and the inside is actually going to be a mesh. So I'll show you that a little bit here if I do a preview slice. So we have a shell thickness here, which is the outside, and then we call this infill. So to get stronger parts, we just want a thicker shell. So right now, our shell is going to be 0.05 millimeters on there, which means we're going to have 2 perimeters on most of the part. We can go ahead and increase that. So if we want, wait a minute, did that wrong. Okay, sorry, that is the wrong spot. So we actually do that with perimeters. So the more perimeters we have, the thicker our shell is going to be. So our perimeters are a particular width, and that's based on our nozzle. We can look what that is. We can look that up right now. So advanced. So our default extrusion width is 0.5 millimeters. So that is the width of one of these lines. So that's the nozzle going around and making a pass. So this part we want particularly strong, so we actually want it to have a thicker shell. So right now we have a 1 millimeter shell because it's 2 passes like that. We can go back to our perimeters, and let's say we want a 2 millimeter shell. If I make that 4, then we can reslice. And you should be able to see now we have a much thicker shell on the sides. Does that make sense to everyone? Any questions in the chat?
Nope, not yet.
Okay. So we also want to do that on the top. So each layer, our layer height is 0.3 millimeters. So we want to make our top and bottom layers consistent with that 2 millimeter height. So if we bring up our calculator here, we've got 2 millimeters and we're 0.3 layers. That means we need 6.667 layers. Now, layers are a finite number, so we can't have 6.6, we need to have 7 or 6, depending on what side you want to err on. So we'll have 7 top layers and 7 bottom layers. And what that'll mean is that our part will have a consistent shell top, bottom, and all around all of the edges. So if we slice this down and take a look at it, you can see that we have a lot thicker walls on all of our parts. So with 4 perimeters, this part is going to be fairly strong, 2 millimeters there. I've seen people go as much as like 7 for very strong parts. Now you're using more material with this and it's going to weigh more. So depending on what you're doing with this part, if you're just making an electronics cover or something, you probably don't need to do 7 perimeters. But if you're making a part that's going to be like actively used out in the field, this is a really good and effective way to make stronger parts. So yeah, you can do very thick parts. This is going to have a very solid layer on it. Does that make sense to everyone in the chat? Please type something if you don't understand.
I'm not getting any questions right now.
Cool. So now we'll talk about infill. So a common misconception is infill is the best way to make a part stronger, and that's not the case. So that's why I showed you the whole perimeter thing, because shells are going to give you a much bigger bang for your buck than infill. So typically, unless you're trying to make a really heavy part or something, you would want to keep the infill low. If you wanted a heavy part, you might move it up to as high as like 80%. 80%. And we'll see what that does. So you can see the grid pattern here is very, there's a lot of material there. It's very fine. Whereas if I do 5% infill, it's going to be pretty sparse. Now the trade-off here is your top and bottom layers may not look as good if you have basically no material inside. So that's why typically I recommend 15 to 20% on the infill, unless you're trying to make an extremely heavy part for some reason. We can also look at the infill type. So grid is going to be your fastest, but we have a lot of different options. So typically we'll use rectilinear or grid are about the same thing. We can do honeycomb. I'll show you guys what that looks like. And honeycomb is going to be very strong on supporting in the X and Y axis. So like the same strong. So if you designed your part really well and you want slightly better infill at no more material cost but a little extra time, we can do a better infill. So this will give you a little more strength and take no more material. So that can be kind of convenient. Another one that's also very common is gyroid. So gyroid is really cool because it actually makes your part strong in all 3 axes. And to show you guys what that looks like, I'm going to get rid of perimeters. So this is what gyroid looks like. So it's kind of it's just a weird pattern of waves and curls and stuff. So this actually makes your part stronger in all 3 axes. So unless we're in a time crunch or just need to crank a part out really fast, you guys are working on a prototype, we'll typically do a better infill than that. So other settings you guys might want to adjust. Layer height's a big one, so I brought that up. With the particular nozzle I have loaded, you typically don't want to go above about 3/4 of the nozzle. So with a 0.4 millimeter nozzle, I don't want to go more than 0.3. We can set printers up to have much larger nozzles. I believe we have one at the school that we can set up to 0.8. And we can do much thicker layers with that. We can print a lot faster and get some good strength increases, but you lose your resolution a lot. So with a part like this, it might be really good because there's not a lot of detail on this part. But with a detailed part, that's not generally going to turn out very well. So hopefully that makes sense. The school has lots of printers. I just use more default settings. So far, are we clear? Everybody understanding how to make parts? And they know how to make strong parts? Any questions in the chat, Kai?
No questions, no comments, nothing.
Cool. So the next thing we're going to go over a little bit is filament settings. So I'll go over all the different materials in a little while. But with our filament, we can do different things. So on your first layer, we generally set a bed temperature. So on an FFF printer, the bed where the printer goes, where the part prints, typically on at least higher end printers will get warm. And you can set that to a particular temperature. And the nozzle where the material actually squirts out is also going to melt. So you need a melting temperature here, and you need a bed temperature here. So based on the different materials you use, you're going to find more optimal settings. So you need to at least hit the temperature where it melts. And you're typically going to find that printing hotter is going to give you better layer adhesion, so it's going to give you better strength of your part. The downside is if you print hotter, you're typically going to have more curling and strings on your part. So usually and you're not going to get as good at bridging and stuff. So usually you have to kind of fine tune that with different filaments. Now, most of the filaments we use, we already know what temperature they print at, and we can get that pretty close. The other thing we have is most of the printers we use have cooling fans on. So depending on the material you print in, you may want the cooling fan on full blast, or you may want to turn it down. So we'll talk a little bit about that, but a lot of this is material specific. So this particular brand of PLA recommends 100%, whereas if I go down to this polycarbonate, it recommends 20%. So it's all material based, and this one actually gets a lot warmer too. Then we can do printer settings, and this is just basically how our printers get set up for the school. So does slicing this part make sense to everybody so far? There's two more things we have to go over. The first one is we need supports. So usually a good thing is we can support everywhere. So now when we slice this, it's going to do supports wherever the computer thinks it needs to. So this will almost always work, but sometimes you're going to end up with supports in places that you don't really want supports. So if it might be very difficult in some cases to get the support material out of the hole. So we might want to do something different. So all supports is pretty good though. And for this part, this would probably be sufficient. But I'll show you how to, in this software release, how to do different things. One of my favorites, it's the lazy way to support on build plate only. On some parts, this works really well. So this is only going to support on the build plate. So these supports are typically easy to move off because you don't have to get them between two objects. So this part worked really well. Now this would not be supported very well if we did that. Does that make sense? So this isn't a good choice for this part, but it would be a good choice for some parts. The other one we can do is support enforcers. So we can actually generate in the software where we want to put supports if we want to design these parts well. So we can add a support enforcer, and typically we'll do that with a box. And it'd be in our part model here. So let's say I want to generate support underneath this piece. I can generate this box and I can make it bigger. So I want to go, say 40 millimeter, we'll do like, see if that's good enough. Position. And then we will. So what this is going to tell it is where this box intersects, I want support material. And then let's say I want to make this longer. So as you can see, I've covered the two places that we can obviously see need supports, and I haven't covered these holes because I don't want to try to take supports out of the holes. And if we slice that down, It's going to pick the intersection points and it's going to generate support. So these are the places I already know it needs support. I've got no choice there. I'm going to have to pull that out. But I think I can generate those holes without support. So now I have made my file so that I don't need to do that. Does that make sense? That's a pretty good example on this part. Any questions in the chat?
No.
Okay. And the last one I want to explain, actually explain on the other one. So I'm just going to delete this because we don't need it. You can save within this slice, you can actually save the whole file so I can bring up with all those support enforcers and everything else. So, but for this, I'm just going to delete these. Now I'm going to add our second part, which is that wheel that you guys saw. So the question is, does this part need support? And that's a question for the chat, so hopefully you guys answer.
We are not getting any answers yet.
No answers. Everybody's confused.
Apparently.
I put everybody to
Oh, here we go. People say no.
No. So, no would be a good answer. This part's actually really cool because this was designed for 3D printing. This particular part was designed not to need supports and print as one piece. Now, we're printing it definitely not on the right side. So, hopefully you guys have realized by now, this part was designed to be print like that, where the base is flat. Does that make sense? Everybody? Hopefully.
Somebody says, is anyone talking? We must have some sort of audio issue.
Well, I think I'm talking. You can hear me, right, Kaya?
Yeah, everybody else can hear you. I'm talking in the chat now.
Alrighty, so this part doesn't require supports. Now I brought something up earlier that explained that small parts on the bed typically struggle to print because they'll come off. And if you look at this part, each one of these rollers is a small part on the bed. So it is going to have a tendency, and having print this quite a few times, I definitely know it does have a tendency to break off the bed. So then you're left with kind of a mess because you've got one of the rollers that have broken off the bed, and usually it doesn't turn out very well. So that's going to bring me to my final trick in the slicer, and that's a brim. So what a brim does is it sets a bigger first layer that you take off later. So it's kind of like support material, removable support for the first layer. So let me show you what this looks like. So you can see this actually gives all of these small areas on the bed a much bigger, fatter surface on the bed. So typically they're going to stick better. So this is really useful for materials that like to warp, which is when they actually pulls up from the bed, as well as materials with these really small first layers. Does that make sense to everybody?
We don't have any questions in the chat, so I'm assuming so.
Cool. So the next thing I want to do is we got a couple more things left, but because the SLA printer is done in the background, I do want to show you guys, or at least get the process started for post-processing that. So can you guys see the printer?
Here, let me try something.
That worked for me. Now I can see my printer.
There, I think everybody sees it now.
So I brought up this is kind of a messy process, and it's also using some harsh chemicals. So I actually use blue nitrile gloves and usually safety glasses to make sure that I'm okay with with this particular part. So when these parts are done, is here we are. They go ahead and they come off the bed. So you guys kind of see that looks like a boat with supports. This is what we generated earlier. So they're kind of messy with resin. They've got thicker things of resin. First thing we have to do is we have to wash them. So this is my little machine to wash it. This has a fan in the bottom of it. And this is a container of isopropyl alcohol, which is the chemical I typically use to clean these parts. So I can start that process. And put the lid on it. And that's got a fan in there, so that's actually going to start cleaning our part. Ooh, somebody sees a printer. That's good. I'm sorry that looks so bad in the video. So now, while we're waiting for this, does anybody have any questions on 3D printing? This is a 2-minute process. And then it actually looks kind of cool. So any questions about this so far? You guys see how this printer works? So we've got a chemical. Oh, there it goes. We got a chemical in the background. That's the resin. And there's a screen. There's a simple screen right there. Actually, so that lights up. So that's actually what cures each layer. So Aaron says, yeah, I see the UV lights. So basically each layer, that's the bottom layer to cure, and then it will pull the part up on the back. This part's done. So what that did is that took off most of the excess resin and made the part look a lot better. So then we'll pop this part off. Now we're left with a part with supports. Like I said, these actually come off. We're left with a couple of these little spots that they just kind of pop off. So we're left with the boat. Now this part, so this machine doesn't fully cure all of the parts that go through it. So we actually have to finish that curing process. And that's why I'm still wearing my gloves as I handle this part, because it does still have wet resin on it and still is somewhat toxic if you were to touch it with just your bare skin. So this little machine has a spring here.
I don't know if you see them, but you have some questions, Alex.
Got questions? How is resin, okay. So do you touch up the surface with some resin in the brush? I generally don't. Usually you actually get a really smooth surface anyway. So sometimes I'll actually go through, and I can do this after it cures too, and just try to, there's little spots on it, you can usually get rid of those. But no, I don't usually do that. And how is resin toxic? It's just kind of a nasty chemical. So yeah, it's generally really bad for your skin. It also smells kind of bad. So I've got an air filter right behind it that's actually taking the smell out of the room, so it doesn't make the room smell terrible, which is probably not good for your health either. So that actually goes through, that shines UV light and it spins the part. And this will take a couple minutes and it'll have the part fully cured. Then you can actually touch it without gloves if it's just a pretty simple plastic part. While I'm here though, I can show you guys some of the other parts that you can do with an SLA cutter. So this one is quite cool. And then if you look, this is a typical example part. And it doesn't come in perfectly. But typically there's hardly any layer lines you can hardly see. There's actually text on the top of this that's really easy to read. So this is by far the highest detail 3D print that we can get for at least standard use. Here's a small horse. It's also kind of cool. So that's about it's a rook. Aaron, who asked in the chat, looks like a chess piece. So yeah, that's the basic process for SLA. So if we need parts that are really high detail, which is sometimes nice, especially that look really nice, or even for like electronics cases and stuff, this is a cool technology to use, and you just get really high quality parts. And the resin that I typically use is fairly weak, just because I get inexpensive resin. There's no reason for these decorative parts to have higher strength resin, but there are some higher strength resins that we can get. So I think the next thing I have, yep. And after about 2 minutes, that part's cured. It's very difficult to see any sort of layer lines on this. The only exception might be on the top, you kind of see it. But yeah, we get a nice solid part. Any questions on that process other than ones that have been asked? Can resin come in different colors? Yep, I've got white and black in the background, but we've got other colors too. So we got lots of different colors for the resins. I really like the look of the white, so I typically go with that. But yeah, there's lots of colors that you could potentially use for resin printing. And different materials. Any other questions? Cool. So I'm going to actually move. To an FFF style 3D printer. You guys see that all right? Aaron says, yeah. So Aaron can see it. Can we see the big castle that you made with FFF at some point? Yeah. Does that work for you? Okay. So hopefully that kind of shows the detail of the things you can do with that. So this took a couple days on this printer. Yeah, it's kind of cool. I swear you guys are Einsteins. I mean, you can buy these. This is just something I downloaded offline. Anyway, back to our work. So I'm going to go over popular materials, and then we'll go ahead and I'll show you guys a quick example print, and then I think we'll be about done for the meeting unless we have more questions. So, screen share. Okay. Popular materials. So let's do that. So PLA is probably the most common printer. The reason being is it's got a really low melting point, and it's really easy to print. So that giant castle that I did was a lot of PLA, just because I wanted it to be as easy as possible to print, and you can get really cool colors with PLA. PETG is also another easy to print material and tends to be a lot stronger than typical PLA. So if you look at this printer, these are actually 3D printed parts that make it up. And those are all done in PETG because the parts are stronger. So that can be really nice. It's also pretty easy to print. It's a little bit more difficult than PLA. The school happens to really like PETG, and almost all the parts you print at the school are going to be PETG. If there's any questions in the chat, Kai, please let me know because I can't see
it. Somebody says, via the dictionary definition of 3D printing, would Legos be considered 3D printing if you go layer by layer?
And designed it in CAD and used a machine to do it? Maybe. So you could probably make a case for a machine that builds Legos to be a 3D printer. I'm pretty sure the internet has somebody has done that. So yes, I believe if you were very clever in how you did it, you could call that a 3D printer. ABS, ASA, so those are really temperature resistant materials. They like to work. They're kind of tricky to print in, but they can have some really nice effects, especially for parts you might want to use outdoors, things like that. And then a fun one is TPU. And TPU is an ultra flexible material, but it happens, it's a little bit tricky to print, but it's printable. Let's see. I thought I had a part around here somewhere. No. Anyways, yeah, we can do high, it's like a rubber material. We also have strong materials. So these are things I think, so here is, can you guys see the camera okay? Or can you showcase the camera, Kai?
Not while you're sharing screen.
Stop sharing. So we can actually do like flexible rubbery parts. So this can be really useful for a lot of different things. Kaya already found a Lego building robot, so cool. What's up? And here's another flexible 3D print. So there's some parts, if you need them flexible, that's a thing that you can do and is pretty popular. Screen share again. Uh, so nylon. Nylon is kind of flexible, not like TPU, but it tends to be kind of flexible. And it's also incredibly strong. It bonds to itself very well. So you can make really, really strong parts on nylon. The downside is it likes to warp on some larger parts. A fix to that, so a subset is carbon fiber nylon. So if you read through a lot of the FRC forums, this is a favorite among lots of teams. So what they do is they'll take a nylon filament and they'll mix in chopped carbon fiber. And contrary to popular belief, that does not make the part stronger. Nylon is just strong. It just makes it less flexible. A lot of times you don't really want a flexible plastic part. So the carbon fiber is going to make it a lot more rigid. It also improves 3D printing. So it tends to work less because the part's more rigid. The carbon fiber is actually reinforcing it down to the bed. So it gets rid of a lot of the heartache there. So a common thing, Markforged was kind of a company to pioneer that. And you hear a lot of teams have Markforged 3D printers. We can do that on our printers too. We can do carbon fiber nylon and get really high strength parts for 3D printing. And these will sometimes be functional enough to replace aluminum parts and give us a lot of flexibility. And then polycarbonate's always one to talk about. So polycarbonate's tricky to print because it really likes to warp. So if you're doing small parts, it works really well, but it's incredibly strong. The wheels our robot uses are made out of polycarbonate, albeit not 3D printed polycarbonate, but just polycarbonate plastic. So it's really common, and this is really good to replace a lot of metal parts. So I think with that, do we have any questions? I'll go back to the chat. If you don't have any questions, I'm actually going to show you guys an example print so you guys can kind of see what the process looks like. And out of all the materials, which one is best to use? I'm going to go with it depends on what you're trying to do. If you're trying to make a really strong robot part, you might consider using something like polycarbonate or carbon fiber nylon or regular nylon. If you're just trying to make a part for just a desk ornament or something, typically you'll just go with PLA. So all materials are good. It just kind of depends on what you're trying to do. Hopefully that answers your question. That's why I talk about all of them. So I'm going to start up a 3D print. It's going to start heating up right now. But hopefully you guys can kind of see what the process looks like. Have you made anything from CF nylon? Yeah, it works really well. Is PETG what we use for most of our parts, like the intake unsticker? So the intake unsticker was made from PLA, and the reason it was made from PLA is because PLA doesn't work. So with that big part and just not wanting to fuss, it was easy to make out of PLA. It's also such a big part that the strength of the material doesn't really matter. So carbon fiber nylon, I've got some of that right here. This is an example part I was printing just to try to play around with it. And it's pretty good. I don't think it's quite as good as a Markforged yet. I'm still playing with the temperatures, but overall, it's pretty nice. It also looks really nice. Here's another part I made for it. So I think there's a lot of potential with that material, and I hope you guys want to try to use it on some robot parts this year because it could be really cool. And this is an example of a nylon part. And it's also pretty strong. You made a Neo. I did not make a Neo. I made an outside pulley for a Neo because I thought that was a cool concept. For those that don't know, the Mini Neo is an outrunner motor. So I wanted to try to actually use the back of it for something. So I did. So it actually bolts to the back of the Neo and spins. So it doesn't use the shaft, it uses the back. So what it's doing right now is it has a sensor, and that allows it to level the bed. So it's taking 9 different points on the bed, and it's measuring the height difference, so it can make a really good first layer. And it's going to start printing. So that's the purging tower, so that makes sure the nozzle's ready. And then it's going to go ahead and start printing. So it'll do one outside layer, and this helps get it primed again and ready for printing. What is it printing? So this is a gear bearing. So this is just one of the default things. So this is several gears all put together that kind of make a bearing piece. It's really just an example print. This one will take a couple hours, so I don't think I'm going to leave my screen up for a couple hours for you to see it. I'll post a picture of it if you want to. Actually, I can probably just pull one up. No, not really, Kaya. Just try to, you can play with some of your over extrusion and try to get it. Don't scale it. If you're going to scale it, make it larger, not smaller. Otherwise, you're going to have a lot of problems with that. And then you've got an extrusion multiplier, try to move that down a little bit, and you might have better luck. Now, I tried doing this on my SLA printer, and I can't get them apart. It actually pieces the parts together. I've not figured out how to do that properly yet. For those that don't know what I'm talking about, that's what I'm talking about. So that's what it looks like. So I think we're about done unless anybody else has any questions. I guess I do have one thing on the shelf. Kind of looks like flowers. Yep. So any other questions for anybody about 3D printing? This was a fidget spinner before fidget spinners were cool. I made this one in 2015.
Okay, well, thank you, Alex, for that riveting 3D print presentation. As always, if you have anyone that is interested in the team, just tell them to email the team email, firstteam4272@gmail.com. And we hope to see all of you next Saturday at 2 p.m.